Let's take a look back at energy diagrams, and I'm talking about potential energy diagrams. There are two types of energy in the universe, potential and kinetic. Which one has to do with the energy of how fast things are moving, and which one has to do with how stable the electrons are? Kinetic is how fast things are moving. That's right. Exothermic reactions create heat, right? Yeah. Faster molecules are hot. Colder molecules are less hot. Don't ever say they're cold. Just, there's absolute zero as the baseline for energy, right? Molecules always have a little energy, so they're above zero. And less stable molecules have high potential energy. More stable molecules have lower potential energy. And potential energy is going to be my y-axis. Potential energy. And we want it to be the y-axis. There we go. And reaction progress is the x-axis. And the two major types of reaction in terms of heat are endo and exothermic. Exothermic means heat's given off. Where'd the heat come from? The potential energy started up high and it went down. Energy is neither created nor destroyed in this universe. If your potential energy is going down, what's going up by the exact same amount? The kinetic energy. But this is not a kinetic energy diagram, it's a potential energy diagram. So in an exothermic reaction, you start high, you go low. And what's that? Somebody said that's the activation energy. That's really good. The symbol for activation energy, E sub A. E sub A equals activation energy. And this one's exo, right? And endo starts low and goes high. Where's the E sub A here? And in general, this is why endothermic reactions are slower than exo, in general. Not always true. The E sub A is always from the origin to the top of the hill. E sub A. E sub A. Énergie d'activation en français. The reason I lowered it is I was going to ask you what lives at the top of the hill. A transition state, TS. TS. Transition state. Yeah. Good. Are transition states the same as intermediate? Intermediates are like the bottom of a hill. Yeah. TS is unique. It's at the top of every hill. And its name is what it says. It says, I am not the reactants anymore. I am not the products anymore. But I'm in transition between them. I'm going to look a little like the reactant. I'm going to look a little like the product. Just like you yourself are a transition state. The way you look now is a little like the way you looked when you were really young. And it's still, inshallah, the way you're going to look when you're a little older. And if we're lucky, we stay looking the same for a long time, right? Yeah. So think about it that way. You're in transition. Your life is the reaction, right? You start off as a little baby and you end up as a very old person. Once again, inshallah. Okay. And the transition is, where you are right now in this overall process. And I like to use you versus me as a good example, because you guys are early in your life, right? You're early in your life. I expect you to look a little more like a young person. And in this room, 100% true. You all look like really young people because you're at an early transition state. Now I got a little gray going on here, getting some wrinkles. Okay. So you got that information to predict that I am at a later transition state. I'd like to think I'm not halfway there, but that would make me very old when I die. So I'm past halfway. Okay. So a later transition state. How does this work with molecules? Okay. There's this dude named Hammond who came up with this. It's a very elegant argument. Try to get it because it's nice. He says, well, you can't look at molecules. You can't say, well, what a young-looking molecule, what an old-looking molecule. You can't do that. What you can do is look at energy. We are very good at analyzing where the energy is. We can construct these diagrams with real numbers for every different reaction. We have the technology and the lab techniques to test these energy diagrams, okay? And energy is easy to measure. So if you find out the transition energy is here, and you knew the reactant energy is here and product energy is here, those are real easy things to measure using calorimetry. We can do that. My question for you, in this first diagram, is the transition state's energy closer to the energy of the reactant or the product? It's much closer to the energy of the reactant, and that's why I drew the transition state box closer. It's on the left, isn't it? Left of center in the diagram, a little bit. Well, it's definitely closer to the reactant. Got this big long tail here. Okay. And this one I drew. Why did I draw the energy? The actual picture where this is closer to this? Because the energy of the transition state in an endothermic reaction is closer to the product. So I expect this transition state to look more like the product than the reactant, even though it still looks like both. That's an old transition state. We call it late. Late transition state, late TS, because energy of TS is closer to energy of product. Okay, and the other one, early TS, because energy of, did I start with TS? Yep, TS is closer to energy of reactants. Now, we can get back to the analogy of people and how they look, which we just discovered, well, realized we can't use that. We can't look at molecules. But, like I said, we can look at energy of molecules. Well, you could do the same with a person. So you pretend you are a person who's got a blindfold on, and you're told somebody's going to enter the room, and your only job is to figure out if they're a youngster or an old person. Okay? And you can't see them. Perfect, right? So if the thing coming in the room, it's a youngster or an old person, you hear a lot of scurrying around. Are you going to be guessing old person? No, you're guessing a youngster because they got a lot of energy. Yeah. And then the next person that comes in, you hear shuffle, shuffle, shuffle. And if they take 10 minutes to get from that part of the room to the other, you're going to guess young person or old person? Old person, right? All things being equal. So you were using energy to base your decision, right? Aren't we doing that here? Okay, so I'm going to give you two examples quick. And I hope this is endothermic. I dot plus, I'm just coming up with, that's not the reaction I wanted, everybody. HI. I want it to be a propagation step. No, it's not HI. II. II. And that's going to give, we'll get the numbers in a second. And this one I'll do ClCl plus the same molecule. No, that's not the same molecule. Not bad. And plus I dot gives Cl plus Cl. Can you get me the numbers? I need Cl, Cl, and II. Let's go get those from page 1. Cl, Cl is 247, yeah, and II 151, 247, 151, 247, 151, 247, 151, plus 151, plus 247. Category is secondary allylic CCl and secondary allylic CI, right? I need those two negative numbers. Why are they going to be negative? I'm making those. Exothermic for making. So we're going to go page 1, tertiary allylic CCl. That's this one, negative 284. And negative 169 we used before. Negative 284, negative 169. 284, 69. 169. Negative 284, negative 284. Was it negative 169? Did I do that right? Okay. So delta H here equals negative 33 kJs per mole. Just, is that 133? Correct? Yeah. They're both exothermic. I had to do better than this. I didn't get an endothermic reaction even though I wanted one. So if I make the bond stronger being made, that'll help. My apologies, everybody. I should have thought about this ahead of time. I'm getting rid of the pi. So which numbers are no longer relevant? Yeah, I agree. Destroying my molecules at the same time. Yeah. If this doesn't accomplish my ends, then I'm secondary CCl versus secondary CI. That is a double bond again because I shouldn't have done that. You're being mean to me. Sorry, not you. Okay. Secondary CCl, secondary CI. I didn't go all the way back, did I? CCl secondary, negative 339, negative 226. 339, 226, 339, 226. 339, 226, 339, 226. Still exothermic. I made it worse. Okay. This is a wasted lecture, but I'm not going to make it wasted. I didn't come up with an endothermic reaction. So it's diagram 1 in both cases, right? Delta H equals negative, we did getting confusing here. 6 minus 5, 1 is 5. 2 minus 5, 7. So they're both exothermic, right? Which one is more exothermic? So more exothermic. Less exothermic. Now, is exothermic early or late? Exothermic is early. Endothermic is late. Okay, but which one is earlier? One on the left. Early and early. Earlier than that. Are we okay? Both early because they're both exothermic. Okay, I'm going to diagram the transition states. We'll still make this a good activity. Okay? It's not an activity. I know. We're practicing. So transition states, you got to have this symbol. I don't know why this is happening. And the question is, what atom is transitioning in this reaction? It's moving from one location to another. Cl is transitioning. And early on, it means it hasn't transitioned very much. Late means it's transitioned almost all the way. So early on, Cl is bonded to Cl. I mean, it's a fact. It's a reactant. It's bonded. It's starting to move away. Starting to move on. And the Cl is starting to make a bond to what? The alkane. So what do these dots mean? Same as they did with the mercury. Those are partial bonds. What's the transition between having a bond and having no bond from Cl to Cl? Say it again, it's the same answer. Partial bond. What's the transition between having no bond to chlorine and a bond to chlorine? It's called a partial bond to chlorine. Okay? And you see chlorine's transitioning. Now, in this one, what's the difference between the two diagrams? This is earlier. Cl still very close to Cl. Isn't that where it was early on? Later. Don't call it late. Later than that one. Still early. Why is it early? Because the halfway point's here. Halfway point. If the iodine was on the other side of halfway point, that would be a delta H that's positive. It's more than halfway to being on the product, isn't it? Late means it's close to the carbon, isn't it? Because it's attached to carbon at the end. So good, even though I couldn't find an endothermic reaction for diagram 2. It's always comparing early, late, and we're good. I think we're ready for an activity.